位老师、同学们，大家好，欢迎来到 NOKOV 度量动作捕捉直播间。本期 Star Talk 直播的主题是多决策智能体的路径规划。首先，我想先向大家介绍一下 Star Talk 的由来和初衷。我来共享一下我的屏幕。好。Star Talk 是由 NOKOV 度量动作捕捉发起，中国自动化学会联合主办，并得到了中国自动化学会混合智能专委会的支持。它旨在促进海外和国内学者之间的相互交流，展示学者们近期的研究成果，分享学术的观点。那前段时间，我们也是了解到，上海交通大学机械与动力工程学院常聘副教授董伟老师和代尔夫特理工大学哈维尔老师合作发表了一篇 IEEE TRO 的论文，题目为《基于粒子的动态环境连续占有地图》。在论文的实验中，采用了 NOKOV 度量动作捕捉系统来记录行人在测试场地中的运动轨迹，并提供精确的速度和位置的数据来作为地面的真值。董伟老师和哈维尔老师都是路径规划、多机器人协同方向的专家。董伟老师主持过多个国家自然科学基金项目、上海青年科技启明星计划项目等。哈维尔老师是多机器人系统技术委员会的联合主席，也是 IEEE TRO 和 Autonomous Robotics 的副主编。今天我们非常高兴地邀请到两位老师，能够以这种对话讨论的方式，向我们展示路径规划领域最新的研究成果。当然，我们也非常的期待两位老师能够在今天的讨论中碰撞出一些新的火花。那在整个直播的过程当中，大家如果有任何的问题，可以在直播间以文字的形式进行留言。两位老师将会在话题讨论结束之后进行统一的解答。好，那下面我们有请今天的主持人，有请董伟老师。
Okay, thank you, Ms. Guo. So first, I will have a brief introduction for Professor Javier Alonso-Mora. Actually, we have got to know each other 3 years ago, and later we have cooperated to publish a paper on the IEEE TRO. And also currently, my first PhD, Chen Gang, is also working as a postdoctor under the supervision of Professor Alonso-Mora. So Professor Alonso-Mora received the PhD degree in robotics from ETH. He is currently an associate professor with the Delft University of Technology. He is also leading the autonomous multiple robots lab. He was also once a postdoctoral associate with the Computer Science and Artificial Intelligence lab in MIT. His research interests include navigation, motion planning, and control of autonomous robots. Of course, with a special emphasis on multiple robot systems. This is also the same as me. He also in his research, he focused on mobile manipulation, on-demand transportation, and robots that interact with other robots and human beings in dynamic and uncertain robot environments. Professor Alonso-Mora is also an associate editor for IEEE TRO and also Springer Autonomous Robot. He was also recipient of several rewards from dynamic and government. So today, let's welcome Professor Alonso for his outstanding research and presentation. So today's topic is motion planning among decision-making agents. So Javier, take your time.
Yeah, so good afternoon, everyone. Good morning. Yeah, for me, it's also good afternoon. So thank you very much for the introduction and also the invite to be here today for this talk. I hope you can hear me properly. I will try to share my screen as well. Hopefully you can see it now full screen, the slides.
Yes, it works.
Okay, great. Yeah, so yeah, again, good afternoon, everyone, and thanks for the invitation to be here today. And it's nice to see you again. So I will be talking about motion planning among decision-making agents. There you see Gang Chen also has contributed a little bit in this area in my group, but this will be the work together with several other people, including him, that are active in my group currently. Yep. So our goal in my group is to work towards this vision that we will have robots that cooperate and interact in shared environments. This could be the cities of the future, but also factories, where we will have robots that provide mobility, transportation, surveillance, and they could be cleaning our streets or helping us carrying something, or our groceries. However, as I think you are all familiar with, we are not there yet, right? This is more of a vision that will be some time in the future, and we are working towards. However, there are already nice deployments that have happened in real life. So two prominent examples are Amazon Robotics, which was one of the first to have coordinated fleets of these orange robots that you see there, providing moving the shelves throughout the warehouses, the logistics centers. And there have been more systems similar to this one that have come to the market after it. We also have displays, shows with thousands of microaerial vehicles, quadrotors in the sky. Here you have one of those examples. But if we look in detail in this, you will see that there are no humans. These are relatively controlled environment and motion. So there are still many challenges. So how do we model complex tasks and environments in which our robots can work? How do we have a real, truthful cooperation for those complex tasks with other robots, but also with humans? And how can we make this reliable and better over time? So I would like to start this talk with an introduction on how do we control a team of robots. So the way that we control, one way to control a team of robots that I also started during my PhD more than 10 years ago, and there you have one example. So we could go from an intuitive high-level specification that this should be understandable for the designer of the system or the one that wants to use and deploy this system. And then it needs to go all the way down to local motion. What you see there were the pixel bots. That was a collaboration with Disney Research, where 50 small robots of controllable light and position are in this case telling the story of the universe. So this was a new type of display where instead of fixed pixels, we have controllable pixels. There you see the sun, the earth, and the moon, and then it will go all the way to the human. So how can we achieve such a system? So the first thing was this high-level specification that should be intuitive for the human. In this case, is the designer, for example, the designer from Disney that will create an animation. The animation is a sequence of images from which we can segment out the background and the foreground. And for the foreground, the fish and the sea in this case, we can compute the goal positions for all the robots in the team. This can be done, for example, in this case with a Voronoi partitioning. Then we need to assign robots to this task. So that's the task assignment. So in real time, we have to decide at 10 times per second or so which robot is going to go to which of these goal positions to minimize the total travel distance. Then there is motion planning. So they need to move safely, avoiding collisions with each other. For that, we use something called reciprocal velocity obstacles. Now, this framework was applied to these pixel bots, but it's very general. So we also have applied it for formations of robots that fly in environments shared with humans, multiple mobile manipulators collaboratively carrying an object, as well as aerial cinematography. with multiple viewpoints with multiple robots. So those are all examples that you see in this slide. Now, all this will follow this structure of these 4 steps. What changes is the cost function that you use, how you define this specification, but the structure is going to be the same for all these systems of controlling a large team of robots. Now, another prominent example that I got interested from my postdoc and thereafter is that of mobility. So in the future, we will also have autonomous vehicles like cars, taxis, but also buses that will be automated, and they will provide on-demand mobility in our cities. This is also a robotics problem, right? We need to decide how to assign the tasks to these robots, and they also need to navigate safely in those environments. So the first step that we have worked in my team is that of task assignment. So that is, how do we decide which vehicle goes to which passenger, and in which order is it going to satisfy those requests when you can combine multiple passengers in the same vehicle. Unfortunately, I don't have enough time today to cover everything, so I will leave out of this talk our work on task assignment. There you have some references in case you are interested in that part. So for the remainder of this talk today, I'm going to focus on motion planning. So that's the lower step on this control scheme. So that how can this vehicle or robot move safely in the environment? And yeah, our goal is to have these vehicles or robots in urban environments. So I think you're all familiar. We have already some deployments of self-driving vehicles in several places around the world, in the US, also in China, and a few places in Europe. In many cases, those are lower complexity environments than what you will experience in a Dutch city. This is Delft, where my university is located. And you can see that here the interaction with the environment is very challenging. So the vehicle will have to reason in real time about the complex interaction with everything else. So pedestrians, bikers, a van, another vehicle. And what the vehicle does will have also an influence. So there is some level of interaction. If our car slows down, they might cross. If our car speeds up, they might let us pass, but we don't know. So the vehicle will need to make decisions in a split second that are safe and reason about this huge complexity. This is driven by a human, so we are not there yet. We are working towards this vision. Now, how does it work? So an autonomous vehicle or autonomous robot will be in an environment shared with other agents like the humans or other robots. It will take some observations. Those observations go into a belief updater and estimator that will tell us a prediction of what everyone else does in the environment. Those predictions then go into the motion planner. So our motion planner is what controls the vehicle. So it will compute, for example, the steering and the acceleration for our car or any other type of input for the robot of your choice. And there are different ways to do motion planning. One of them that I will be focusing on in this talk, because we use it a lot in our group, is that of a trajectory optimization. Now, how does trajectory optimization work? And in particular, receding horizon trajectory optimization. You will also see people referring to it often in the literature. We refer often to it as model predictive control as well, MPC. So there we have a horizon n, so that's typically a few seconds in the future, and we want to minimize a cost function. So there is this j that will be the cost in every discrete stage in the future, and the terminal cost at the end of the planning horizon, again a few seconds in the future. This cost function could be anything, for example, to follow the middle of the lane. Then this will be subject to a set of constraints to satisfy the dynamics of the vehicle or the robot. And then we will also have the collision avoidance constraints that the state needs to always be safe. And this makes it hard because then it's a non-convex optimization problem. And but luckily there are solvers nowadays like Forces Pro or Akados or IPOP that can solve such a system, such an optimization problem, if you give the appropriate cost function and constraints. And here you have two examples from our work. On the one side, you have a quadrotor with a payload that is hanging. And on the other side, you have our self-driving car from TU Delft that is avoiding a pedestrian that was not paying attention. So in both cases, we are solving this MPC problem with different cost function and constraints. And this running several times per second, so around 10 Hertz or faster. Now, are we there? So we are not there yet. So MPC has shown to be very powerful, but there are still several challenges that we are facing. So the first challenge is that of uncertainty. So how do we model uncertainty? So that's the world is not deterministic. So the previous formulation that I showed here, this was a deterministic MPC. So this can work well if you have a very fast replanning horizon, but in reality, you have to account for the uncertainty of what the others will do. You don't know exactly what the pedestrian is going to do, for instance. So then the collision avoidance constraint will become a probabilistic constraint, where we say that the probability of being collision free needs to be greater or equal than some bound 1 minus epsilon. And then there are some tricks that you can do, for example, a scenario optimization or formulating deterministic chance constraints from a Gaussian distribution to solve this problem. Another challenge that we face is these planners plan a motion for just a few seconds in the future, so they need also global guidance. Otherwise, they can get stuck in a local minima or not find a feasible solution in a very complex, crowded environment. So the next challenge that arises is how do we provide global reasoning to these planners? How can we provide them guidance? And this can be done, for example, by exploring multiple homologically different paths for the robot. And then the third challenge that arises here is how to model interaction. So the interaction means that the actions that we compute for our robot will also have an influence on everyone else. You see here an example from the Netherlands again. It seems a challenging environment when you drive by bike in the Netherlands, so I don't recommend it to the first-time tourists, especially in Amsterdam. It can get crazy. But you can see here that everyone needs to really reason about the interaction. So how does my action affect others? Will they let me pass or not? And if you do it wrong, you might get stuck like that biker there. So this is what I'm going to focus in the remainder of this talk on how do we model interaction and how can we solve for the interaction in our planners. And yeah, and then again, another example from the Netherlands, now autonomous, so these are boats. So we also have a project for autonomous boats, and you can see that a normal day in summer in the Netherlands, in Amsterdam, can get very crowded also. And there is very complex interactions happening here between the different drivers of the boats. Now, what changes when we want to model interaction? So this is the diagram that I showed before of an autonomous robot or an autonomous vehicle. So here, when we model interaction, what happens is the actions of the autonomous vehicle or robot have an effect on what the other agents are going to do in the future. So this is modeled by these red arrows now with the policy pi. So that's the policy that controls our vehicle. And we need to also close the loop between the perception and the planning, because the plan that we compute for the next 2 seconds or more for our robot, we should also reason about how will it affect others. How will they react to this plan that I'm computing? And this makes it much more challenging because then there is a coupling between the motion planning and the perception, the prediction. So one way to approach this problem that we have done recently is to formulate a dynamic game. So this comes from game theory. And I will use this example of we have our self-driving vehicle and a pedestrian there. And what we want is we want to minimize some cost function, right? To compute a trajectory, and we have to reason about both the robot R and the human H. So that's why we have now both indexes here, because we have to reason about what is the future prediction, the future trajectory of the human, as well as the one for our vehicle. And we, this will be the state and control trajectory. And then we want to minimize some cost objective function that now depends on both the trajectory for our robot and the trajectory that we predict for the other agent, like the human in this case. Now we have to solve this optimization problem for both our robot and the human. And that's what is illustrated here. But there are some constraints that will couple both problems. The collision avoidance constraints is a clear coupling. If the human goes to the right, then the robot will have to go to the left, for instance. And this is what we see here. And when we solve this optimization problem, this couple optimization problem, we will solve it for the generalized Nash equilibrium. So this is an equilibrium where none of the two agents independently has a benefit to change the strategy. There could be multiple of those. So one Nash equilibrium could be this one exemplified here, that the pedestrian goes to the right. Another one could be that the pedestrian goes on the opposite side. So there could be multiple of these Nash equilibria. But we solve it for one of them, where none of the agents has an incentive to do something differently by itself alone. And then we are going to solve this again in a receding horizon fashion. So this is called model predictive gameplay. So similar to model predictive control. So it follows the same ideas. And then one challenge here is how do we model this cost function? Because we can define the cost function for our robot, but we don't know the intents of other agents, and we need a cost function for them because we are assuming that they are rational agents. So we need to create a cost function for them as well. So one way to do this is by parameterizing that cost function with a parameter, in this case, theta. So this parameter could be, for example, indicating whether the pedestrian goes right or left. So those could be the two parameters of theta. And then we can maintain a belief over these intent parameters. So this belief update, you could use a particles filter or a Kalman filter to keep track of this belief over time. And that belief, then you can plug it back into your cost function to get the cost function of the other agents with that real-time updates on the belief of the parameters theta. Now, this is, games have been out for a while. So one thing that our contribution in this case was we proposed contingency games where we are going to plan with the current uncertainty, but we will also anticipate the future certainty that will happen. So we assume basically that at some point in the future, we will have certainty. So before this branching time, TV, we don't know whether this pedestrian goes right or left. We just have some belief about it. That's what is displayed here. But after this branching time, we assume that we will have full knowledge on whether the pedestrian goes right or left. And then at that point, we only need to commit to the one that we have observed. So this could be the case, for instance, when a vehicle is potentially taking a left turn. So initially you don't know, but at some point you will know that it has started the maneuver to turn left. So this will have to come from the sensors, this branching time as well. So it's an estimate of when will you get that information. Now, how to solve this problem? It can be done by formulating a joint optimization problem, like the model MPC problem, receding horizon optimization problem that I showed before. So it will be formulated with both the trajectory for the vehicle and the trajectory for the human. And then you can formulate the KKT conditions and solve this optimization problem with existing commercial or academic solvers. And that, when you solve that, I will not get in details in this talk on how do we actually solve it. But basically, you will just formulate that optimization problem and give it to a solver that will output the optimal trajectory for your vehicle up to the branching time, and as well as the ones afterwards, so the red and the blue that you see in this figure illustration. And also it gives you a prediction of what we expect the human or the other agent to do when they interact. And in the video here in this animation, you can see some examples where the belief is changing from having a higher belief or likelihood that the human goes to the left versus to the right or in the middle. And you can see how that adapts the plan that we compute for our vehicle. Now, another way to solve this type of problems, an observation that we have made is that this interaction that you see here is the same equations that I showed before. So it's the same interaction problem, but this type of problems, MPC, can also be solved by sampling trajectories. So the advantage of sampling trajectories is that then it's gradient free, and you can also parallelize taking samples. While if you do it through a solver, you will need to compute gradients. So you will need your cost functions to be differentiable. So that is an advantage of solving this problem sampling based. And what does it mean sampling based MPC? So we refer typically in the literature to it as MPPI. So for model predictive path integral control. So that's how it originated. And the idea is as follows. So the idea is relatively simple. So we have our robot, in this case, the vehicle, the green vehicle that wants to go to the goal on the right. And what we are going to do is we are going to take samples. And how do we take samples? The way that we take samples is by sampling from a noisy input distribution. So we have a probability distribution of our inputs for our system. So it could be the acceleration and the steering angle. And then we are going to take samples from those distributions. So we are going to sample input sequences. We are going to forward simulate all of those sequences. So this is what we call rollouts. And we collision check them. We compute a cost for each of them. So these are the ones that you see in gray. And so we evaluate their costs. And then we compute the importance sampling weights for them. So those that are better will get higher weights. Those that are worse, they will get lower weights. And then what we are going to do is we are going to approximate the optimal control input for our vehicle with the weighted sum of the sample trajectories. And this will be, then we apply the first input as it's done with the standard MPC. And we are going to repeat this over time. So the robot will move a little bit. We will take new samples from an updated probability distribution based on the computed weights in the previous step. And then we continue doing this again and again. And again, the nice thing of such an approach is that you can sample from any distribution, and you can evaluate with any cost function, basically, your rollouts. Now, of course, we were wondering, can we also use this for interaction? So can we also model the interaction with other agents with MPPI? And then we came up with this interaction-aware MPPI, where the idea is simple, or well, it's not simple, but it's a modification of the original MPPI. What we are going to do is we are getting rollouts, so we are taking samples from both our robot as well as the other agent. So instead of taking only rollouts, samples from the robot, and taking a prediction of the other one, we are also going to compute the prediction within our rollouts by computing rollouts for both of them. And the way that it works is we choose a local goal so this can be for our robot. And then we also need to predict the goal for the other agent. This prediction can come from a constant velocity prediction, or it could come from a neural network that predicts how the other agent is going to move. And then what we do is we plan the motion by solving the joint optimization problem by taking rollouts for both agents, so for our robot as well as the other agent, the other cell vehicle in this case, or it could be the human. And then we are going to apply to our robot the first input that we compute. And the rollouts for the other agent, those can be used as an interaction-aware prediction. And then you will again repeat this many times per second. Let's see an example. So here you have an example from this approach. So this is completely distributed. There is no communication between the different agents here. It's an intersection in a canal. So this is for autonomous boats on a canal. It applies to other robots or self-driving cars. And the orange vehicle, that one is our autonomous vessel. And it's navigating this urban canal of Amsterdam among 3 other incoming traffic vessels. And you can see that they were able to reason about their interaction and find a solution where it can avoid the other 3 vessels in a socially compliant manner. That because it can model this interaction by computing rollouts and interaction-aware predictions for the other agents as well. So this was solved with interaction-aware MPPI, and is fully distributed without communication. Now, MPPI, it's more powerful. So it applies also for other types of robots. So one example was the autonomous boats that I showed, but we have also applied it to mobile manipulators, like the one you see there in simulation, picking an object from a table, and also for the other, the manipulator that you see in the right within the AI for Retail Lab, where we were able to push objects or pull objects as well and move them around the table with these rollouts from MPPI. Now, if now you like it very much and you decide, oh, MPPI is awesome, I'm going to implement it in my robot. So one thing that you have to be careful or aware, and if you already work with MPPI, this will resonate with you, is that the way that you take samples is very important. So this example that you see in this video, this is a standard MPPI, where we throw a box in front of the robot, and what happens? The robot collides. Why does it collide? Because the the distribution of samples was not wide enough. So it was relatively narrow. And then at some point when the box goes in front of the robot, all our samples are invalid. So all of them lead to a collision. And then the robot doesn't know what to do. And this is because we are sampling around the previously feasible trajectory. So if there is a drastic change in the environment, then your sampling distribution could completely fail. Luckily, there are ways to solve this. So what we propose is to use ancillary controllers. So as you see in this video, now the robot is capable of avoiding the box, even for these very unexpected situations. And this is because in every time step, we are taking one sample. So one sample is from a predefined controller. So in this case, there will always be one sample that is the controller that says stop. And then normally that controller, that single sample will not have any effect because it's one out of a few hundreds. But when something unexpected occurs, that one sample will get a very high weight, and then it can bias your distribution of samples and resolve the problem and continue moving safely, as you see in this example. Now, so overall, MPPI is a very powerful method. However, it can require extensive computational power. You need to take many samples, you need to evaluate all of them. So it's very well posed for solving in a GPU, for instance. And then you can get, good performance, but it will require quite some computational power. So we were also wondering ourselves, can we have something faster, more reactive, that we can use for highly dynamic and interactive settings? And then what we came up with is something called the dynamic optimization fabrics for motion generation. So this one is a bit of a different type of methods. So this one is a geometric method in which there is no horizon. So it's a very reactive method. However, it's super fast. You can run it at 1,000 hertz even, so 1,000 times per second. And it can control all the degrees of freedom of a mobile manipulator, a complex mobile manipulator like the one that you see in these videos. And you can have, therefore, very fast reactive planning. And what our contribution in this case was to be able to follow time parameterized trajectories, like the one you see that mobile manipulator following the green dot while avoiding the red sphere and avoiding those obstacles. And the use case was for a stocking robot in a supermarket, while there are also people in the supermarket. So these methods, the optimization fabrics, are very powerful for high dimensional systems and very fast. And they can be your lowest layer for collision avoidance. On top of this, then you can have a higher level reasoning, for instance. You also have the QR code there. So we open source the code of this and many others. So MPPI, we also have an open source repository that you can check. Now, where are we going now from this? So we recently hosted the RRS in Delft. So the Robotics Science and Systems Conference was in Delft this year. And there we show this demonstration. So this is where we are going now. So we are working with multiple mobile manipulators that are able to grasp, pick objects, and coordinate their tasks. So in this case, we are deciding which robot does which task, and that they can also adapt how to do those tasks in real time and avoiding each other. So they need to do this safely in an environment shared with other robots and later on with humans. So for now, we are not there yet. For now, you see here an example. So this is both of the robots are using optimization fabrics. So that's the whole body control method that I showed in the previous slide, modified in order to avoid each other. So this is where we are going. So this is within the ERC Interact project, where we want to have robots that can work in environments shared with other robots and humans, both reasoning about the tasks as well as the motion planning. And with that, that brings me to the conclusion or the end of this talk, where I have talked about several topics. So I started with an overview of how can we go from a human specification for a team of robots to individual motion. So here the goal was to control and design the motion of a team of robots. And we saw that we can use different types of methods, and then we will need to do a task assignment followed by a motion planning, collision avoidance. Then I went more in detail into the motion planning part of such a problem, and in particular, how can we model the interaction in motion planning, the interaction with other agents or traffic participants. And I discussed 3 types of methods. So the first one was contingency games. So contingency games, it's an explicit way to reason about the interaction. We can have multiple hypotheses. That's what we show with the contingency, right? And we could also infer the objectives of other agents, for instance, with inverse games. So this is the formal way to formulate your interaction problem, because you are explicitly formulating the problem with the other agents and your robot. And we can solve this with model predictive gameplay and formulate your constraints, your cost function, and then use existing solvers to solve that problem. Another way that I discussed was to sample. Instead of solving the optimization problem directly with an optimizer that requires differentiable functions, we can also take samples. We can solve the problem with MPPI by taking samples of trajectories for all the agents in the environment. And then we are going to do weighted sampling of these future trajectories. We can have an arbitrary cost function, so there is no need for differentiability. However, we might need a reasonably powerful computer to be able to take those samples in real time. And we have to be careful, how do we take the sampling distribution? And the last part that I mentioned is that I cover in this talk is interaction with other agents is very important, but our robots will also more and more interact with the environment. And for that, we have mobile manipulators, mobile manipulation, which will also be able to, in the future, open doors, bring things around and move things and work more closely with other robots and humans. And there I discuss geometric fabrics as a very fast reactive geometric way to encode behaviors. So this could be the lowest layer for a whole body control of a mobile manipulator. And on top of that, then you need some guidance. And that will be task and motion planning in environments shared with humans. And with that, I would like to conclude this talk. So thank you very much for listening. Thank you also to the sponsors of the work that I showed here. And yeah, now I'm happy to answer any questions that you may have.
Okay, thank you, Javier. So maybe first I will have a small discussion with you. Okay, so there are many online audience, but I think some of you, maybe most of them, are not in the field of multiple robots. So first, I would want to ask you to have some explanation for them. For example, some of them, maybe they are familiar with drones. For example, the night show, there are maybe thousands, hundreds of drones. They are fly together. But for this kind of system, they are controlled by something like a central computer. But for us, we study the multiple robots. They are not in this same architecture. We use different principle. So I want you to explain the basic knowledge for them. Something like you give some examples, or just for like some comparison. Thank you. Okay.
Yeah, thank you. Thank you for the question. So, well, first of all, I would say I also consider this a multi-robot problem. And what I cover for me is also multi-robot in the sense that as you were saying, there are 2 types of multi-robot systems. There are the ones that is centralized, that one central computer controls everyone in the system. But we will also have more and more systems where there are multiple robots that they have to implicitly coordinate. So, or explicitly. So they could communicate. So they could communicate trajectories. That's something we have also worked on. For example, with distributed MPC, so distributed model predictive control, and consensus techniques. So you will have that every robot communicates, and then they agree on a common objective and a common way to solve things. The other way, that is what I covered in this talk, was how do they coordinate when there is no communication? So this could still be seen as a multi-robot system where there is no explicit communication. So that will be the case when, for example, we don't allow for privacy or whatever communication between the robots, or you have different self-driving cars on the streets that they are from different companies and they are not going to be talking potentially with each other. So we have seen, research has shown that if they communicate with each other, it's going to be more efficient, but it's unclear to which extent. And we will always have still humans, pedestrians, bikers that will not communicate. So it depends very much on the application. So if you can have a central computation unit that controls everything, the performance will be much better, because then you know perfectly what everyone is doing, right? And then you can solve for that joint optima. If there is no central, for example, in warehouses. So warehouses is one example where you can have a centralized system. The shows in the sky is also a centralized system where you have one computer that can give commands to everyone. But that's not always the case. I don't know if that answered your question, but if not, I'm happy to follow up.
Yeah. Okay. So the second one. So as you have mentioned that for multiple robots, maybe we can communicate with each other or not. Maybe sometimes we don't need to communicate with each other. But for this is for between robots. But for your research, you mean you have to use the robot. It should be react to the motion of maybe human beings. So maybe there is. Do you think there are some similarity between this robots without communication and this kind of robot and human being system? Do you think what's the difference or the or maybe the common feature? Yeah.
So that will be the difference between the also humans, or between or how can we use this type of methods where there is no communication for a multi-robot system? I think you meant the latter, right?
Yeah. I mean, yeah. Okay.
Yeah. So, well, I think another important aspect is scalability. So, if you recall at the beginning of the talk, I showed the pixel bots. So those were the 50 small robots that were displaying images, and we were coordinating their motion and the color to display images. And there, the system itself for collision avoidance was using something that I mean, it was a very simple version of what I explained later on, but it was also with assuming no communication. So it was using reciprocal velocity obstacles, which is a method that does not assume communication. So the assumption is that everyone cooperates. So that's an assumption that we can make when there is no communication, that every robot has the same algorithm, for instance, that every robot is using the same algorithm or a similar algorithm. And then we have constraints that make them, that the solution is collision free. When they independently compute a solution. So that's what we were doing with reciprocal velocity obstacles. And the advantage of doing that is that it's scalable. So I only show it with 50 robots in real time, which 10 years ago was a very nice thing. We were one of the first to have really 50 or so robots in a nicely coordinated manner. But we also had real-time simulations with thousands of robots. And that's the advantage of having a distributed system. That you can make it much more scalable. And the other advantage, obviously, is if the other ones are not robots or that they don't communicate, right? But even in a multi-robot system, it can have advantages to reduce the communication. If they also communicate, like in consensus, they will also have to use a lot of the network. The bandwidth of the network can also be a problem. If they communicate a lot, they can saturate the network. The network can also fail. So you can jam the network, for instance. So there are many things that can fail with communication. So another area of research that I didn't cover in this talk is how do you reduce the amount of communication? So if there is communication, how do you decide when to communicate? With which other robot do you communicate? At what information do you share? And that's one place where learning is a powerful technique. Yeah.
Okay. So here I have one more question. Maybe on your slides. Maybe here like the maybe page.
Shall I share them again?
Yeah. You can share this again. Yeah. Thank you. Yeah. So I know maybe on page 12 you use MPC, right? And later you use something. Yeah. Page. Maybe we first go to page 12. The 12th page. Yeah.
Yes.
At the very beginning, maybe you use MPC, right? Page 12.
This one, I think, right?
Yeah. This is at the beginning. This is purely on MPC, right? Yeah. And later you use something like dynamic games. But I noticed that you plan this Okay, later you use something like dynamic games.
Yes.
Yeah, later. Yeah, maybe next maybe several pages. So, but I noticed I don't know exactly the page. Maybe page not still maybe the next page. Dynamic game. Yeah, like this. But yeah, I noticed that maybe you plan this trajectory with two stage, right? Something like two stage. You mean you have a short term planning and or maybe like a global planning? Am I right or not?
Not exactly. So,
Yeah.
well, the way we solve this in the background, yeah, I'm sorry I didn't have time to go in details. So one can find all the details in the references that I had throughout the slides. But this problem is then formulated like the original MPC in some sense. So we also discretize the trajectory over a time horizon. So that the discretization is going to be, for example, 20 steps for a horizon of 2 seconds, let's say. So that will be a trajectory like the one that you see in the image. So it's there are multiple stages in one plan. So it's one trajectory, one discrete trajectory with multiple stages that we compute. Now, maybe what you are also referring to is this contingency game where we have a branching time. However, here it's all in one single optimization problem. So it's not that we solve first a bigger problem and then a second stage another sub problem. We solve one single optimization problem where we formulate the here it was a hidden slide, but let me see. It should still be there, I think. No, it's not in this slide deck, sorry. Yeah, I don't have here the slide with the details, but yeah, it is one single optimization problem where we optimize, we discretize the trajectory. And what we will solve here is we basically will formulate two trajectories. And in the optimization problem, we will have both trajectories. So we will have variables for the blue trajectory and variables for the red trajectory. And then we have a constraint that says that until the time horizon, until the branching time, both trajectories have to be equal. And after the branching time, both trajectories can be different. So we do that by having constraints.
Okay,
Did I clarify?
Previously, I just noticed this TB. So I think maybe you plan this. Maybe you have two stages. That is, the first one is before the TB, and the second one is after the TB. Okay, so
so we kind of have two stages, but the two stages are together in one optimization problem.
Okay. So so I have another question on this one. So what's the difference? So previously, maybe I have so for me, maybe I will solve this problem. I first model this kind of human beings, the motion. I will use something like Gaussian distribution to model this motion of the human beings, and then I use an MPC to plan the trajectory. So what do you think the difference is? How to say if I go deep, if we go deep, so what's the difference between this approach?
Yeah, so the core difference is whether interaction is explicitly modeled or not. So, well, there are two differences, right? So if you have just a Gaussian prediction for the pedestrian, you cannot model that it goes right or left with some probability. So in that case, you will only assume that it goes right or left. So because otherwise you need to have a multimodal probability distribution. And the Gaussian cannot encode this right or left behavior. So you will need to have a sum of Gaussians or another type of multimodal distribution. So that will be the first difference. So here we can have multiple hypotheses. So a multimodal probability distribution. That's the first one. Now, assuming that the probability distribution was also Gaussian, the difference is in the model of interaction. So if we play this video again, let's try to put it full screen again. So if we play this, if you carefully look at the pedestrian, you will see that the trajectory of the pedestrian is not straight. So you can see that the trajectory predicted for the pedestrian, it is also going a bit upwards, like now. So that comes from solving the game, because the game is saying that the pedestrian also reacts. So here, then we see explicitly that the pedestrian is also going to react to the vehicle. It will move a little bit to the upwards in this case because the car is coming from the bottom. And that's the solution of the Nash equilibrium. If you were to have just a Gaussian distribution for the pedestrian and then give that as a constraint to the MPC, then you will see that the pedestrian is just going straight and the car will do the full avoidance. Now, which of the two approaches is better or worse? That's so the game is the explicit way to model interaction. Solving it with just a Gaussian plus MPC would work also well in many cases if the control loop is high enough. Because the advantage of MPC is that with high control loops, it can adapt to changes in the environment. So at the end, it will also depend on how crowded it is, how dynamic and interactive your environment is. So maybe with just one pedestrian, you will not see much of a difference. But if you have a very crowded area, then you will see that the interaction becomes more and more important. Is it clear?
Yeah, very good.
Okay.
So the last topic I want to discuss with you. Okay, so I think this is how to say the common difficulty between us. Of course, I also do some research for the maybe perception and planning. So for the perception, there are many. How to say we can't find a standard scenario to test our algorithm. Maybe I will test this in the woods or in something like in a building. I will have some result to show that our robot works well. Okay, so we can publish paper, and later I give some presentation so to show our results to maybe some other professor. So some professor from maybe like mechanical engineering or some professor from traditional control engineering. They will ask me how to guarantee the your performance in maybe in general scenarios. For them, for example, for the control engineering, they will have some standard criterion, something like a steady state error, something like overshoot. But for us, we don't have this one. Maybe in different scenarios, we have different dynamical obstacles and something, or maybe they said other things, also different. So how do you think we should answer such kind of questions?
Yes, I mean, this is a complex topic, right? So
yes.
If we look in carefully under the hood on what type of warranties do these algorithms have? So we are for solving a constraint optimization problem. So we have explicit constraints. So if we find a feasible solution, it's warranted to be collision free or to whatever those constraints say, right? So that's assuming that, and only for the time horizon. So here there are two challenges. So one is the problem could be infeasible. So it could be that with the time that you give to your algorithm, it cannot find a solution, or the environment is too complex. So it can fail to find a feasible solution. And that's one problem, that it's very hard to guarantee that it will always find a feasible solution within a time budget. Another one is the horizon. So you will need recursive feasibility. So if you design a controller for a dynamical system, then you will want that if you have an MPC, it's recursively feasible, which means that if you find a solution that is feasible for one step, in the next time step, when you recompute, you will still be able to find such a solution. Now that also it's very hard to guarantee in these complex settings. So the best that we can do is I think is to say that if we find a feasible solution, it's going to be collision free for the time horizon that we compute that trajectory, right? And that is also going to be up to the model that we have of the environment. Humans might behave in a different manner, right? So it's very challenging, these dynamic environments, because there is uncertainty from the environment that also will need to be modeled. and having warranties in such an environment, therefore, is extremely challenging due to the computational cost. So for some small problems, this can be warranted. For example, one could, colleagues of mine are using, for instance, control barrier functions. That's one way to have some explicit warranties or other formal methods. The problem is that those methods typically only work well in constrained environments, so simplified environments, and so on. In the complexity of the real world, it's very hard to have any hard warranties, I would say. And with respect to how to verify or test our algorithms, so for computer vision, so everything that has to do with the perception, there are data sets. And then you can just test your algorithm in those data sets and you say, well, in these data sets, it works very well, right? That doesn't mean that in a different data set, it will also do very well, but at least there are some data sets. For motion planning, this also becomes very hard because then you need a simulator. So you will need a simulator that simulates and runs your algorithm and then compares it in a set of scenarios against other benchmarks. And we don't have such benchmarks in our community, in part because it's hard that we all agree on which ones are those problems. Everyone modifies a little bit their problem for the application where they want to use their motion planner, and then it's harder to compare different methods. So having good benchmarks will help, right? So having good benchmarks when you can upload your methods and they will be evaluated in those benchmarks will help.
Okay. So thank you. So
I'm sorry, maybe it's not the answer your colleague would like to hear, but
maybe we can
if it's your colleague and you want to convince them, you can tell them that our methods are very good, and if it's feasible, it finds a very good solution.
Okay. Yeah. Okay. So here we also have some audience, and they are online. They also have several questions. So I will read this for you, and maybe you can ask them. So the first one, he asked, will distributed MPC lead to convergence difficulties? So is there any difficulty to analyze? Or just guarantee the convergence of distributed MPC?
Yeah. So yes, it can be warranted convergence under some assumptions. So it depends on your overall problem. So under some assumptions, yes. It could still take very long. So it depended on the problem. So my experience also with distributed MPC, where you have to communicate the trajectories and iterate until there is convergence, is that sometimes a lot of communication effort is required, a lot of iterations, and that makes it impractical in real life, because your robot cannot be waiting very long until this convergence. Those are challenges with distributed MPC. So the amount of rounds of communication and the amount of data that you need to communicate, and whether it converges or not, that depends on the specific problem. So how complex is your problem? Yeah. So for example, whether it's linear or non-linear, right, or convex or non-convex, all that will have an effect on whether you can guarantee convergence or not, and whether that convergence is to a global minima or a local minima. Hopefully, oops, am I frozen or? I think I froze, or at least it's very quiet on my side. Sorry.
Okay, Javier, Professor Javier, Professor Dongwei maybe have some.
Okay, I'm back. I think.
Oh, okay.
Okay.
I'm back.
Sorry,
I don't know what happened. It looks like it froze. I think it
there are
froze.
some problems with my connection. Okay, so the second question, maybe you have just answered my question, but you can still briefly answer this question for our audience. So, is the multiple agent fully autonomous or teleoperated?
Well, I mean, in our work, it's all fully autonomous. So we have not worked on teleoperation. Yeah, and other people do, other colleagues of mine, they work on teleoperation. And teleoperation of a multi-robot system is also complicated. The reason is because there are many degrees of freedom. And some of the tools, well, we have done also a little bit, but the challenge here is that you will need to reduce the number of degrees of freedom. So a human cannot control every robot individually in a multi-robot system. So you need to think about ways to allocate the tasks to the human and the robots, or to reduce the number of degrees of freedom. So for example, the human gives high-level commands to the team of robots, and then you have some autonomy in this team that will do the task by itself with only some sparse global input from the human. So those are challenges that appear when we have a human swarm interaction or human multi-robot interaction. So how do you go from this complexity of many degrees of freedom from the multi-robot system to something that the human can understand and give proper inputs to the system? So it's not something that I work much in my group. We did organize a workshop on human multi-robot interaction in IROS last year. If you search for it, I think you will be able to find the website of that workshop. It was in IROS in Detroit last year. And we have a list of speakers that are working on that field. So those could be good pointers for you. Yeah.
Okay. So the third question. So can decision making solve problems in trajectory optimization? I think he wants to ask, can we just use decision making to solve the problem instead of trajectory optimization? Yeah.
Yeah. I mean, well, it depends what you mean by decision making, right? So my guess here by decision making is it means more like an MDP, so like a Markov decision process that then maybe you solve with a learn function, like a neural network or some other type of learning method, right? So that's my guess. Correct me if I'm wrong, or adjust the question accordingly. But the way I see this is that, well, game theory at the end, this trajectory optimization game theory is also decision making. So it's not the way that we even teach it in our course is that game theory is it's an extension or a particular case of after we look into how to solve Markov decision problems, which is a decision making problem, right? So there are links and similarities between what is decision making and what is trajectory planning or trajectory optimization. So, and then there are different ways to solve that optimization problem. Now, if the question is about learning, so I typically believe more on a two-layer approach where we have high-level decision making or learning for things that are a bit slower or need global guidance. So to reason about the complexity of the world, for example, with semantics and with everything, right? So that's very hard. We cannot encode that into a motion planner trajectory optimization. So we can use neural networks and other things from decision making to guide a motion planner. So that's something that we have done also in my group a little bit, and what we are trying to go that we use learning and tools from decision making, for example, in the cost function of your trajectory optimization. So for example, in that terminal cost function or and so on, where then it provides global guidance. Now, why do we still need trajectory optimization? I will say that there are some very important reasons. One is we can have explicit constraints. So we can have explicit constraints for collision avoidance, for the limits of the joints and other things that are very important that need to be satisfied. We need to reason about the dynamics of the robot, and that needs to be explicit. You don't want the robot to do stupid things. And that also links to the fact that these motion planners are quite reliable. So if things change a little bit in the environment, they will still behave nicely and properly. much better than a neural network, for instance, that you don't know what will happen if things change. Yeah, I tried to answer your question in two ways. So hopefully one of the two was the one that you meant. Otherwise, you can ask again.
Yeah. Also in this in the meeting room, maybe here is a chat. Chat room, you can also read those kind of questions. Okay, here still maybe we have two questions. So this one maybe concern about this computation efficiency. Okay, he asked, is replanning is frequent enough? I think he wants to ask, how about the computation efficiency? Also, here is there any time delay which will how to say affects this planning?
Yeah. Okay. So, well, it depends on the method. So, for example, optimization fabrics, so the whole body control that I showed at the end of the presentation, that one is super fast. So that runs in 1000 hertz or so. You can run it, so like 1000 times per second. So it has no problem because you basically pre-compute a controller and then it's just evaluating it in real time. If we look at the other methods, so like MPPI or dynamic games or MPC, so MPC, the standard MPC, it's the fastest one. We can run it in a few milliseconds. So I think nowadays you can run MPC at, I don't know, 5 milliseconds or so. So that's pretty fast. If you also solve the game or run MPPI, then maybe you can run it only with current software, with current hardware at 10 hertz or so, so 10 times per second. But we can still run it in real time and replan. Now, with respect to the delay, and this, of course, will depend on the complexity, right? So, for example, the game theoretical problem will depend on the number of other agents that you account for. So the more other agents you take into account, the larger your problem is and the longer it will take to compute. So that is a drawback of such methods. That's also something where learning can be used to speed up things. Now, I think there was another part of that question that I forgot now.
Okay, so maybe someone mentioned about the time delay.
Yeah, the time delay. There was the time delay. So the time delays, normally, I mean, the time delay is not a problem in these cases because of the fast frequency, replanning frequency, right? So if we replan 10 times per second or so, and it's not super dynamic, so I mean, if you want your quadrator to do flips, then that's another story. Then the time delay itself is not so problematic. If it is problematic, then there are ways to estimate the time delay. So if you estimate how long your algorithm is going to take, so if you give a time budget, you can then compensate for this in the predictions. So you could then make all the predictions with this compensating for that time delay. So there are ways to handle the time delays, as long as you know how long, as long as you can estimate them, right? And as long as you can be consistent in finding a solution within that time budget.
Okay, so here, there, I think this is the last question. So, can we find an optimal result for planning with this MPPI? And if not, or can we just estimate its error bounds? Error bounds, yeah.
Well, so if we look at the original work on MPPI, so model predictive path integral control, then there we will see that what we obtain, so this weighted sum of inputs, that's the optimal solution of the probabilistic problem. So if you have a system with noise, if you have a dynamical system with noise in your inputs that does some task, then it can be proven and shown that this weighted sum of sample trajectories is the optimal solution of such a problem. So in that sense, theoretically, yes. Now in practice, yeah, we abuse it a little bit. So it's modified a little bit, the way that we solve it with respect to that original work. We also cannot take infinite amount of samples. So Yeah, and also the variance is limited, right? So I was also talking about the distribution of samples. So we will not be able to find a global optimum of the optimization problem because of that distribution of samples. You will need to sample everywhere, and then this will be impractical. So yeah, there is a difference between theoretical warranties for optimal control of stochastic systems and the practical warranties that we get in our robots and systems.
Okay. Yeah. Sorry. Here
And
we
sorry, one more thing. And with respect to bounds, yeah, we don't have a bound, so it is very hard to have bounds. And I think that's true for many algorithms in robotics. Having bounds is very hard because then either you need to be able to you need to compare it to the optimal solution, and that's also a very hard problem. Yeah.
Okay. Yeah. Okay. Here we sorry. Here we have a new question. Okay. I think this is the last one. So this guy asked if replanning is frequent enough. So is prediction or predicting other agents states still necessary? I think he wants to ask if we can replanning very fast, can we just use MPC because we just plan each step, step by step, very fast. So can we still use the prediction? Still use the approach? Yeah, I think he want to ask this.
Yeah, I mean, we also use MPC in many cases, right? So I started the talk with MPC, and I showed two examples of MPC, one of a self-driving car and the other one with a quadrot or with a pendulum. So yes, in many cases, one can directly use MPC, even with a constant velocity prediction. And this is yet another topic. So to which extent do better predictions mean a better planner? We don't really know. So we have seen again and again that having a better predictor doesn't necessarily mean that your planner will perform better. So my take is, well, the first approach is always use a constant velocity prediction and an MPC. And if that works, then you are done. Then problem solved and then move on. In many cases, that will work well. However, there are some interaction-rich environments. So for example, if you just want to do collision avoidance, maybe that's enough. If you have a racing problem where you have quadrotors or self-driving cars that will be racing with each other, then you need to model the interaction because the prediction, a constant velocity prediction, is not going to be sufficient. Or if you have a robot that moves in a crowd of people. So if you just use constant velocity predictions, then you will have things like this robot freezing problem and so on. So your robot will just stop and not move or not know what to do. So it depends on the complexity of the environment. Yeah, we have a paper in IROS in 1 week or 2 weeks where we try to analyze the complexity of environments. So that's from one of my master students, Mochi Shi. Also with Clarence Chen, so your previous PhD student. So there we try to give some metrics on the complexity of dynamic environments. So I would say if it's not very complex, then a simple prediction and MPC will work quite well or very well.
Okay. Yeah. Thank you very much. I think today our talk can stop here. So later maybe I will still ask Miss Go to maybe they will have some conclusion, and also maybe he will have some prediction for the next session. Yeah. Thank you very much, Javier. Hope we can see you in the future, in the near future. Yeah.
Yeah, for sure. See you soon. And thank you everyone for attending.
Yeah. Okay. Bye.
Bye-bye.
Okay, many thanks to Professor Javier and Professor Dong Wei. 非常感谢董伟老师和 Javier 老师的精彩对话。那也是看到有同学在直播间提问，就是我们本场直播的这个回放。我再给大家共享一下屏幕。好。 那大家可以关注度娘的机器人世界公众号，并在这个公众号上面回复直播回放，就可以获取到我们这场直播的回放内容。那刚刚在我们直播间进行提问的同学，也可以在这个公众号上面与我们进行私信联系，获取小礼物一份。我们也是非常感谢你们的参与和支持。那接下来呢，我将介绍一下我们在 IROS 2024上New Generation Star Project 这个的活动。在 ICRA 2024大会主席王志东老师的指导下 ，NOKOV 度量动作捕捉发起了 New Generation Star Project 的活动。王志东老师呢，他为我们提供了极为有力的支持和建议，在此我们也是特别的感谢王志东老师。New Generation Star Project 它旨在为优秀的青年学者提供展示学术成果、促进学术交流、扩展他们职业发展网络的这么一个平台。在 IROS 2024上，我们将会继续征集优秀的青年学者，那么入选者将会受邀参与 IROS 2024的官方答谢晚宴，并在晚宴上展示他们的研究成果。我可以为大家就是分享一下我们在 ICRA 2024上就是 VIP dinner 上的这个现场的实况。
We have a sponsor to take down the new generation star in our place.
Also, we are honored to launch the new generation star project here.
Professor, please keep up with 5 years old.
Hello, everyone. I'm Li Xingdong from Delft University.
I'm Dr. Fei Gao, an associate professor from Zhejiang University. My research interests include aerial robots, autonomous navigation.
Lai Xiang from Tsinghua University. Gao Fengli is the director of the arts lab from Zhejiang University.
Explore cutting-edge AI and robotics at the Image Processing and Robotics Lab.
And Chang from Peking University, and my research centers on reproduction perception lab at Rio University.
Hello everyone, my name is Yi Tianbi from the Shenzhen Institute for Robotics Technology.
好的，那除了在晚宴上进行成果的亮相展示，我们也将通过 Star Talk 直播、度量访问等方式，对 New Generation Star Project 的入选者进行持续的宣传和交流的推动，并且在 IROS 期间，我们还组织了一个老师间的社交 party， 这样会为国内外的优秀的学者间的相互交流提供一个平台。那目前 IROS 2024 New Generation Star Project 已经启动了招募，欢迎大家扫描屏幕上的这2个二维码进行报名申请。此外呢，在9月18号，我们将会组织一场聚焦海洋环境真实试验、卫星信号拒止海洋环境智能无人系统的直播活动。我们邀请了哈里发大学自主机器人系统中心创始人兼主任拉格玛教授，以及北京理工大学宇航学院及哈里发大学研究团队来分享和讨论。请大家关注度量的机器人世界公众号，回复直播进行预约报名。那我们本期的直播就到此结束了。我们非常感谢大家来到我们的直播间，也感谢中国自动化学会以及中国自动化学会混合智能专委会的支持。感谢大家的收看，那咱们下期再见，大家再见。